Hello and welcome back to my channel. So this video will be on design of two-way continuous slabs. Last week I made a video on one-way continuous slabs and you guys are requesting to make a video on two-way slabs also. So here it is, design of two-way continuous slabs. So before we start, we'll just do a quick overview of what it is and what we have to keep in mind before we start designing the slabs. So a complete detail of this is given in IS code page number 90. It's on page number 90, annexure D or something. I'll show you that. So here it is, it's in annexure D, it's on page number 90. So I'll quickly go through all the important points. So the clause D 1.1 says the maximum bending moment per unit width in a slab are given by the following equations, that is mx, that is moment in shorter direction, is alpha x, the load per meter square, into Lx square, it is a smaller span, and the span bending moment in the longer span, that is my, will be alpha y w L x square only. So you can see that the difference between the two is that even for the bending moment in longer span we use the shorter span direction, that is Lx square. Now I'll show you what is alpha x and alpha y. Before that you have to keep four things in mind. So that is long edge, short edge, continuous and discontinuous. Now why I have written you, I'll show you that. Now suppose this is a slab, this is a two-way slab. Let's assume this is Lx and this is Ly. So in this, the short edge will be Lx and the long edge will be Ly. Now what is discontinuous and uncontinuous? Now if there is a slab right next to it, then this edge will be considered as a continuous edge. If there is no slab beyond this point, beyond like this, if the slab is supported over here on a beam and that's the end of it, so this edge will be considered as a discontinuous edge, that is that the slab discontinues there. And suppose if there was a slab over here also, then it would be considered as a continuous edge. This edge would be considered as a continuous edge. Similarly, if there was a slab over here, this edge would be considered as a continuous edge. Now it can be short edge continuous or long edge continuous, or it can be short edge discontinuous and long edge discontinuous. So this you need to keep in mind before calculating alpha x and alpha y. I'll show you that now. So guys, if you haven't subscribed to my channel, please go ahead and subscribe to my channel because I post videos like this every week, so please make sure to subscribe to my channel. So how to calculate alpha x and alpha y? So as you can see in this table, that is table number 26, there are certain conditions given over here. So this case 1, case 2, case 3, there are 9 cases. Now there's condition written over here, one short edge continuous. That means the shorter edge of the slab is continued over to the next slab. If it says two long edges continuous, means out of the 4 sides, the 2 long edges are discontinuous, means the slab with the long edges discontinuous or ends there. 3 edges discontinuous means the slab is supported on only one side and all the 3 edges are discontinuous. So this is very basic common understanding. I think I don't need to go into the depth of this. So just let's continue back to the topic, that was design of two-way slabs, and once we start off with the problem, we'll understand what is the conditions and how to calculate alpha x and alpha y. Okay, so one more thing that you need to keep in mind is that in case of continuous slab, there is negative movement at the supports. Okay, so suppose if this is the slab and this is the continuous edge as well as this is the continuous edge. Okay, so if I draw the bending moment diagram of this slab, it will be negative moment over here at the support and positive moment at the center. So it will be somewhat like this. So you need to calculate negative moment here, here and here, and for that we need alpha x and alpha y. Fine. So in this case there will be mx positive, mx negative. if this side was Lx. Okay, if this edge was also continuous, and if it was Ly, then there would be my positive and my negative. My negative would be here and my positive would be here. So let's start off with the problem now. So this is a floor system given to us. There are 3 slabs actually. S1 and S1 slab is a similar slab, so there are in reality 4 slabs, but the design has to be done for only 3 slabs. So S1 and S1 are similar, so they can be designed in a group, and S2 slab is there and S3 slab is there. Now all of these slabs are two-way slabs. Now S1, S2 and again S1, these all 3 are continuous, and again S2 and S3 are continuous over here. We have to use M30 concrete and Fe415 or steel. Okay, so let's proceed with the problem. So first we will design slab S1, and if you haven't watched my video on design of two-way slabs, please go ahead and watch that video, because I'll be going quickly through all the small points, so I'll not be going into detail of that. So please watch that video so that you can get an understanding on how I solved that step in detail. You get the understanding over there. So the first step always in the design of slab is fixation of depth. So D will be equal to span upon the basic value is 26 for continuous slab multiplied by MF. So span over here will be 2000 divided by 26 into MF. I will assume MF as 1.3. So as you can see in the slab S1, the smallest span is 2 meters, so we will take the smallest span always for the calculation of depth. Now this will give you 59.17 mm. Now this is the effective depth. Now for safety purposes and for fire safety concerns, we will take D as 100 mm and overall depth capital D as 125 mm. Now once you get the depth, second step will be load calculation. Now I will take live load as 2 kN per meter, floor finish as 1 kN per meter, and the self weight of the slab will be the density of RCC concrete, that is 25 kN per meter cube, multiply by the cross section area, that is 1 meter multiplied by 0.125, that is the overall depth, and that will give me 9.125 kN per meter. Sorry, this will be 3.125 kN per meter. So if you add all of this, and you will get it as 6.125 kN per meter, and this is working load. For getting the ultimate load, WD will multiply it by 1.5, and you will get it as 9.18 kN per meter. So now you have got the load for the slab. Now this load will be same for all the slabs, so we will not calculate this step again and again. So this load will be used for all the slabs. So now the main step, that is calculation of moments. So as you can see, I have drawn a figure of the S1 slab. Now as you can see, the S1 slab is continuous on this side. So it means that the shorter edge of the slab is continuous, and all the 3 edges are discontinuous. So the bending moment over here will be negative moment on the fixed support and the positive moment at the center for Ly direction, and this is the Lx direction. That was 2 meter. And for this side, the bending moment diagram will be just like a simply supported beam. Now before calculating alpha x and alpha y, you will need to calculate the aspect ratio, that is Ly by Lx ratio. So in this case it is 3/2, and that is 1.5. Once you get this, you have to go to the table number 26. I'll show you that now. So this is the table number 26. The alpha x and Ly by Lx ratio is given over here. So in our case it is 1.5, so we will refer only this column for alpha x, and for alpha y we will refer the last column. So it will be same for all the conditions. Now depending upon the conditions, in our case the one short edge was continuous, so the case will be case number 8, that is 3 edges discontinuous and one short edge continuous. Now for alpha Ly by Lx 1.5, the alpha x is 0.076 and alpha y positive is 0.043 and alpha y negative is 0.057. So I'll write it down on the paper now. Now alpha x positive is 0.076, alpha y positive is 0.057 and alpha y negative is 0.043. Now the formula for bending moment for x direction is alpha x WL x square, and for bending moment in y direction it is alpha y WL x square only. So see the difference, that is x over here and x over here, so don't take Ly over here. So mx positive will be 0.076 into 9.18 into Lx is 2, so 2 square, and that will be 2.79 kilonewton per meter. Similarly, I'll calculate for my positive and my negative. So naturally mx negative is 0 because it is 0 here and it is 0 here. So I've written down all the moments for my positive and my negative. You can see how the calculation is done over here. So these are the moments I got. Now the steel for this and this will be different. So I'll calculate from the formula, that is AST equals to 0.5 FCK over Fy 1 minus under root of 1 minus 4.6 M FCK BD square into BD. Now you will take mx positive here, my positive and my negative. For all the three cases you will get AST x positive, AST y positive and AST y negative. So here are the steel ASTX, that is 78.15, ASTY positive is 63.55 and ASTY negative is 47.6 millimeter square. Now before you provide the steel for this, you need to calculate what is the minimum area of steel that is required in the slab, because maybe the AST minimum will be greater than all of this. So if you provide steel for this and if your AST minimum is greater than that, then your slab may fail and it may not be as per the guideline of the IS code. So the AST minimum for slab is 0.12% times the cross sectional area, 0.12% for Fe415 steel. So I have solved it here and it is 150 millimeter square. Now this is greater than ASTX and ASTY, so you have to provide the minimum steel over here. Now before providing steel, we will calculate the steel for S2 and S3 first, then we will decide what steel to be provided in the entire slab. So next we will design slab S2. We will repeat all the steps that we calculated for the previous slab. The first is fixation of depth, and the formula is span upon 26 into modification factor. 26 is basic value for continuous slab. So the shorter span is 2 meter, so 2000 divided by 26 into MF. I'll increase the MF over here because this is the center slab, so the load transfer from both the slab will be quite higher for this slab. So I have increased the MF over here, and the depth will be 66.67 mm. You can also take 1.3. There's no hard and fast rule over here. So for safety purposes, I'll take D as 100 mm and the overall depth as 125 mm. Now the second step is load calculation, and as I told earlier that the load on all the slabs will be same. So the design load, I'll take it as 9.18, which was same for the previous slab also. Now again the next step would be calculation of moments, and for that we need to see what are the end conditions or the condition on the edges. So I'll show you a figure on the next slide. So as you can see in this figure, the slab S2, one of the short edges is discontinuous and all the three edges are continuous. So as you can see in this slab, that is the S2 slab, one of the long edge is discontinuous and all the three edges are continuous. Now for this condition we'll see what is the alpha x and alpha y in table number 26. So I've drawn a figure over here. Now if for L y direction, so this is 2.5, that is the longer span, and this side is 2 meter. The bending moment will be fixed support पे negative moment, and it will be somewhat like this: negative here and positive here. And for this side also, for LX direction, it will be negative moment here and positive moment over here. So we need here alpha x positive, alpha y positive, alpha x negative and alpha y negative. Then we'll calculate Ly by Lx ratio always, that is 2.5 divided by 2, and this will be 1.25. Now we'll see the table number 26. So as you can see in this table, the case number 3 says one long edge discontinuous, okay, and it doesn't say about all the other edges. So if it says one long edge continuous, it naturally means that all the other three edges are continuous. So for this case, and our alpha Ly by Lx ratio was 1.25, so that is in between 1.2 and 1.3. So you have to interpolate over here, or you can just make an assumption, which I have done here. So for negative moment at the continuous edge, the alpha x will be 0.052 and 0.057. It will be somewhere in between these two values, and the positive moment will be 0.039 and 0.044, somewhere in between that, and the alpha y positive will be 0.028 and alpha y negative will be 0.037. So I'll write it down on the slide now. I'll show you how to interpolate also, okay. So let's take for alpha x positive. Now we have alpha x for 1.2 and 1.3 only. We need it for 1.25. So for 1.2 it is 0.052 and for 1.3 it is 0.057. Now what it will be for 1.25? Let's assume it is x. Now to find x, you will use this relation: 1.3 minus 1.2 upon 1.25 minus 1.2 is equal to 0.057 minus 0.052 upon x minus 0.052. So it is this minus this upon this minus this is equal to this minus this upon this minus this. So if you solve for x, you will get the value for 1.25. So I have already calculated alpha x and alpha y, and alpha x positive is 0.0415 and alpha x negative is 0.045. Then alpha positive is 0.028 and alpha y negative is 0.037. Now from this we'll calculate mx positive, mx negative, my positive and my negative. Now I'll just solve one for sample. So mx positive is alpha x positive, that is 0.0415 multiplied by w, that is 9.18, multiplied by lx square, so that is 2 square, and that will be 1.52. And similarly mx negative will be 2 and my positive will be 1.02 and my negative will be 1.52. Now you will use the same formula for AST, that is 0.5 FCK for that formula, and you will calculate AST x positive, AST x negative, AST y positive and AST y negative. Now I have already calculated it, and I'll not show you that. Not show you the calculation, but I'll write it down over here. So here are the value: AST x positive is 42, AST x negative is 55, AST y positive is 30, and like that. and this is the formula that I use in case you want to know. Now if you compare all of these with AST minimum, which was 150 millimeter square, now it is far less than all of this. Sorry, it is AST minimum is greater than all of this, so we have to go for AST minimum. Okay, now we have the steel for slab S1 and S2. Now we will design slab S3, and that will be the final slab. Now the next is design of slab S3. So this is just S3 slab. It is 4 by 2.5 meter. The shorter span is 2.5 and the longer span LY is 4 meter. Now if you see this plan over here, the S3 slab, in the S3 slab, the shorter edge, that is 2.5 meter, only one of the shorter edges continuous, but all the three edges are discontinuous. Now for this condition you have to look for in the table number 26, and accordingly you will have to calculate alpha x and alpha y, positive or negative, whatever will be the case. Now again the first step is to fix the depth, and the formula is span upon the basic value is 26 for continuous slab into mf, and the smaller span is 2500 upon 26 into, let's take we'll take the same mf, that is 1.3, which was for S1, and that will be 72.46 mm. We'll take d as 100 mm and overall depth as 125 mm. Now second step is load calculation. We don't have to calculate the load again, as the load on all the slabs is same, that is WD is equal to 9.18 kilonewton per meter. So in this slab, S3 slab, this edge was continuous while all the rest edges were discontinuous. So in this case the bending moment will be, for LY span, will be negative over here and positive at the center. So the bending moment diagram would be something like this. So we will need alpha y negative and alpha y positive, and for this side it will be 0 at the edges, so we only need alpha x positive. Now before we go to table number 26, we need to calculate the aspect ratio of the slab, that is Ly by Lx ratio, and that will be 4 divided by 2.5 and it will be 1.6. Now let's proceed to table number 26. So as you can see in table number 26, there is case number 8. It says 3 edges discontinuous and only one short edge is continuous. So in our case it was, so this was the short edge, so this was the short edge and this is the long edge. So this edge is continuous while the other 3 edges, that is 3 edges, are discontinuous. Now for that case the positive alpha, now let's see the Ly by Lx ratio. For us it was 1.6, so it is in between these two. So similarly for alpha x, it will be in between 0.076 and 0.087, while the alpha y negative will be 0.057, alpha y positive will be 0.043. Now you have to interpolate for 1.6. I'll not show you that, I'll just write it down, you have to do that. So here are the alpha x and alpha y values. Alpha x positive is 0.082 and alpha x negative is not there, that is 0. Alpha y positive is equal to 0.043 and alpha y negative is 0.057, and using these you have to calculate mx positive, mx negative, which is 0, my positive and my negative. So mx positive will be 0.082 into 9.18 into 2.5 square, and that will be 4.7 kilonewton meter. Similarly I'll write down my positive and my negative. So here is my positive and here is my negative, and these are the formulas that I use in case you want to know. Now once you get mx and my, you have to calculate ASTx positive here, ASTy positive here, and ASTy negative over here. ASTx positive I have calculated and it was 132 millimeter square. ASTy positive was 68.82 millimeter square, and ASTY negative is 91.77 millimeter square. Now again, all of these are far less than the AST minimum value, and which was 150 millimeter square. So we will go for AST minimum again here. Now I'll summarize all the AST values for S1 and S2 and S3 slab. Now this is a table which shows ASTX and ASTY for slabs S1, S2 and S3. Now for S1 slab, the ASTX and ASTY steel was less than AST minimum. So I'll take 150 for ASTX and 150 for ASTY, and similarly for S2 also it was far less than AST minimum, so I'll take AST minimum as 150, that is 150 and 150 here, and again 150 and 150 over here also. So throughout the same slab we can provide the same type of steel. Now let's provide 10 mm steel, so the spacing will be area of one bar, that is pi by 4 into 10 square, divided by the total steel that we have to provide, that is 150, and for per meter width of slab, that is 1000 mm, and that will be 523 mm. But the minimum spacing criteria for main steel is 3D or 300, and 3D is 125 times 3 or 300. So we'll go for the minimum value, that is 300 over here. We can't provide for 523 mm, which is exceeding these two. So let's provide 10 tor at 300 center to center on in both ways. Now one thing you have to remember, that in case of 2S slabs, once again I'll show you a figure and then I'll explain. In case of 2S slab, there is always a negative moment at the support. So what we do is we will bend half of the steel and take it into the supports. So for the bending moment at the continuous edge will be somewhat like this. Now what you have to do is, you need steel at the bottom over here, you need steel at the top here, and at the top here. So what you do is, you will alternatively bend up the bars. So if this is a straight bar here, what I'll do is, near the support I'll bend it up and take it into the support. Similarly, the next bar would be straight from this side, it will go straight, and when it comes to this point, it will bend up and it will be taken up into the supports. We don't need bars over here, okay, because already the moment over here is 0. Okay, so what we need is the steel over here to resist the bending moment, that is positive bending moment here at the bottom and the negative bending moment at the top. So we have taken the steel at the top. So it will be 10 mm bars at 300 mm center to center, and it will be alternatively bent up. I'll show you a cross section diagram so you can understand it much better. So I just made the section detailing of the slab with hand. So this is S1 slab, this is S2 slab, and again this one is S1 slab. I'll show you how the section is made. So the section goes like this, and you are looking at that side. So as you can see, I've written it as 8 tor at 200 center to center because I wanted to make a change over here, because when I solved it for myself I took it as 8 mm, but for change I took 8 mm for the video. So it doesn't matter, you can write it down 8 tor at 300, which was for our case, 10 tor at 200 center to center. Now these are the bent up bars that are taken up into the support, and this is the extra length, that is LD, provided to transfer the stresses. I'll make a new video on that, why LD development length is provided in steel. So this is 3 meter, 2.5 meter, and again 3 meter. So this bar goes straight, and again this bends up and goes into the next support to a distance of L by 3, and again this bar bends up and goes into the next support for a distance of L by 3, and this bar is bent up at a distance of L by 2 from the supports, and that's it, and that's what you want to know. And these dots that you see there, that is the steel in the other direction, which is same, that is 10 torr at 300 center to center. Similarly, you can draw a section for slabs S2 and S3 as well, and this is what it is. If you don't know how to detail the slab, the reinforcement in the slab, I'll link the video in the description. You can watch that video, and if you haven't watched the two-way slabs video, please watch that also to get a better understanding. And that's all with the design of two-way slab. I hope you understood the problem completely, and if you have any doubts, please comment down in the comment section below, and don't make sure to like the video and subscribe to my channel.